Okay. So, in the last lectures we have discussed the few concepts like open set, closed set, perfect sets, boundedness of the set in a general metric space. Today we will continue with the same with certain results related to these sets and also few properties of this. So, before going, let us see that which is already known, the segment AB. B means set of all real numbers x such that a is strictly less than x less than b. Then this set we call it as open sets, open interval. Then segment AB means set of all those real numbers where a is less than equal to a, less than equal to b. This is the closed interval, and these are the semi closed intervals. Set x belongs to R such that a is less than equal to x, less than b. Left hand it is bounded by the right hand side is open, while this is right hand side bounded and left hand side open. So, these are the semi closed intervals x less than equal to b. These are. Now, we define the K cell in the space R K as follows. Let us suppose if A I is strictly less than B I for I equal to 1 to and say k, then the set of all points, then the set of all points x having the coordinate x 1, x 2, x k in R k, whose coordinate satisfy the inequalities A I is less than equal x I is less than equal to b I for I is lying between 1 and k, each called a K cell. Is called a K cell. So, the meaning is that suppose in case of R 1, say R 1, the one cell means an open interval, A 1 less than x less than b 1. So, this is a one cell A 1 and b 1 and all the points coordinate. So, basically this is the collection of this point x such that x lies between this. So, it is basically a set of x belongs to R such that x lying between A 1 and B 1. While in case of R 2, the two cell means the set of those interval x is say x 1, x 2. These are the points in R 2 such that x 1 lies between A 1 B 1. Sorry, this is equal to also B 1, while the x 2 lies between A 2 B 2. So, it means this is like a rectangle. Say this one is our rectangle. This is x axis, this is y axis, and here is this rectangle. So, the points here is these are the points. Say here is A 1 B 1, and while this point is A 2 B 2. So, x 1 lies here, x 2 lies here. So, it is basically the range inside this a rectangle closed rectangle bounded by. So, similarly, in case of R K, we have a K cell, the concept of K cell. Now, the concept of the open wall or the closed wall. Open wall or closed wall B in R K cell, in R K space is defined as the set of all defined as the set of all y whose distance in R K of course metric, in R K metric from x is a point in R K, is strictly less than R, is strictly less than R, and when it is equal to R, then it is called the closed wall, and this is the open wall centered at x with radius R. So, it means the V centered at x with radius R in R K space where the x belongs to R K is the set of y 1 by 2 say by k belongs to R K such that d of by x in R K is strictly less than R. Then this is the open wall, and for closed wall, and for the closed wall it is less than equal to x belongs to R such that d of by x is less than equal to R. This is in R K is a closed wall. So, we sometimes denote also is a B bar x R, closed wall for this. Okay. Now, we define the convex set in R K. We call a set E subset R K, subset of R K set to be convex. A set is convex, is said to be convex if lambda x plus 1 minus lambda y belongs to E whenever x, which is x 1, x 2, x k belongs to E, y, which is y 1, y 2, y k belongs to E, and lambda lying between a real number lying between 0 and 1. So, this set is said to be convex. It means, this is our set say E. Take the 2 point x and y, and if the line segment joining these 2 points, that is the lambda x plus 1 minus lambda y, this is the set of all point in between x and y, because lambda lying between 0 and 1. So, entire line segment if it also lies in E, then we say set E is convex in this set. Okay. Obviously, this convex set will always result, or as a examples are every ball centered say B x R open ball, I am choosing open ball, is convex, every ball is convex with centered x and radius R. The reason is because if we picked up the 2 elements from this ball, say y and z, let y and z belongs to the open ball centered at x with the radius R. Okay. Then by definition d of by a in R k, because we are choosing in R k of course, is less than R, d of z x in R k is less than R. Then what is a, if I take the linear combination, means a line segment joining y and z, if it also these every point on it this line segment belongs to the ball, then ball will be a convex set. So, consider this set, we are consider the distance of lambda x plus 1 minus lambda y, sorry, y and z, lambda y plus 1 minus lambda z distance from x, isn't that is equal to mod, we are denoting mod of lambda y plus 1 minus lambda z minus x, and this is in R k. So, need not to write R k, but I am just putting to avoid the confusion, because this mod does not mean here the simply the absolute difference in as we say in the real line. So, since the metric is taken from the R k, so this mod means under root of this coordinate x 1 minus y 1 square, x plus x 2 minus y 2 plus x n minus y n square of this. This is the meaning of this mod. Okay. So, this will be less than or equal to lambda times mod y minus x plus 1 minus lambda times 1 minus lambda times this is 1 minus mod z minus x. Just adding and subtracting here x and here x, we are getting the same thing. Okay. Then mod minus 1 minus lambda, but y and z are in ball. So, this is less than r plus 1 minus lambda into r, and that will be nothing but what is less than r. So, this shows the line, the point lambda y plus 1 minus lambda z is in the ball centered at x and radius r, and this is true for any arbitrary point y and z, where y and z is an arbitrary point of the ball. So, entire line segment belongs to this, where lambda lies between 0 and 1. Therefore, ball is convex set, is convex. This we will require it. So, we are giving the concept set. Now, we have seen the concept of the open set, closed set, etc., in the general metric space. So, we also have few results say in the form of example or maybe the theorem. The theorem says every neighborhood is an open set, So, proof is, let us consider a neighborhood centered at P with a radius r, where the P is a point in R. So, we are taking say neighborhood, I am just taking in the form of that suppose circle maybe, but it may be depend on the space in open set. So, suppose centered is P with the radius say R. We want this neighborhood to be open. It means every point of this neighborhood, if it is the interior point, then it will be open set. So, consider a point Q in this neighborhood. Let Q belongs to NRP. Okay. Then say there is Q. Find out its distance from P. So, one can find. So, there is a real positive real number h such that the distance from P, distance between P and Q is r minus s, because Q is inside, obviously the distance will be less than r. So, h can be obtained, so that the distance is exactly this. Okay. Now, we wanted to show that there will exist a neighborhood around the point Q, which is totally contained inside this NRP, then NRP becomes open. So, consider the set or neighborhood around the point Q with a radius h. Say this is the set of all S belongs to NRP belongs to S such that, not NRP, with this we will show it in there, such that distance from this QS is strictly less than H, is in R, this is in R, okay, real line or RK space if it is so, okay, in RK and so on, or RK, any one of them, clear. So, this we wanted is entirely contained in this. So, let us find out distance. Consider the distance of this S is somewhere here, S from P, then this is less than equal to distance from S to Q plus distance Q to P, but distance S to Q is less than H and this is R minus S, so total is R. It means the distance of S from P is less than R. So, this implies that S is an element in RP, NRP, neighborhood of the point P with radius R, and since S is an arbitrary point basically in the disk, in this disk with radius H. So, entire neighborhood, the neighborhood NQH is totally contained in NRP. This shows NRP is open, because the point will be interior point and Q is arbitrary, and since Q is arbitrary point. So, every point is an interior point, therefore, it is an open set. So, this shows Q is an interior point. Okay. Clear? This is open. This subset means Q is the interior point, H, or because Q is interior point by them, and since Q is arbitrary, therefore, it is completely open. So, this was another results also, which is also useful. If P is a limit point, P is a limit point of a set E, then every neighborhood of P contains infinitely many points of E. Many points of E, sorry. What he says is that suppose this is a set E, okay, and P is somewhere here, say P, this is P. Now, this P is a limit point of the set E. If we draw any neighborhood around the point P, suppose I draw any neighborhood around the point P, then this neighborhood will contain infinitely many points of P. Then, if P is a limit point, then any neighborhood around the point P or every neighborhood of the point P will definitely include infinite number of points. If it is not, then P cannot be a limit point, that we will show by. So, in order to prove this thing, we will suppose that there is a neighborhood of the point P which does not include the infinite number of points, but includes only finite number of points, then we will lead a contradiction. Okay. So, let us suppose there is a neighborhood, say capital N of P, which contains only a finite number of points only a finite number of points of E. Say these points are Q 1, Q 2, Q n. So, let Q 1, Q 2 and say Q n be those points of n intersection E, because this n, this is our set n. So, n intersection C will be this set. So, this contains only finite number point q 1, q 2, q n, which are distinct from P. Okay. So, now what we do? This is our point P, here this is say neighborhood n, and here is something like E. This is our E. Okay. So, here are the points q 1, q 2, q n and so on. So, these are the points say q 1, these are the point q 2, these are the point q n, these are the points. Now, what we do is we find out the distances of these points from P. So, let us find the distances d of these points q m, where the m varies from 1 to n, and then find out the minimum distance from this P, that is m 1 is less than equal to. Find out the distance from q 1 to P, q 2 to P, q n to P, and among all these 10 find out the minimum one, find the lowest one, say, and this distance is suppose r. Let r be this. Now, if we construct a neighborhood, take the neighborhood centered at the point P with the radius r, then this neighborhood means set of those points x belongs to the neighborhood belongs to n intersection say E, such that distance of P to x is strictly less than r. So, obviously, once you get this thing, then what is this? This set will be empty set, because x should be different from P, because there are in this neighborhood, this is the neighborhood n intersection E, it contains only the q 1, q 2, q n's, only n point, and the distances are taken from minimum distances r. So, if we find a neighborhood or point whose distance is still lower than r, then we do not get any point except P itself, but we want the P, the point should be different from P. So, basically there is no such point an empty set. So, P is not element. So, this neighborhood does not contain point of E which is different from P. So, this implies, so this neighborhood does not contain a point Q of E which is different from P, does not contain any Q which is different from P. So, P cannot be a limit point, because by the definition of the limit point, if P is a limit point, then every neighborhood of P must contain at least few points of A, at least some point of E, which is so this contradiction. In contradiction is because our wrong assumption that a neighborhood there is a neighborhood which contains only finitely many points, only finite number of points. So, this is wrong. This implies that the every neighborhood of P will contain infinitely many points of E. This proves the results. Okay. Now, as a corollary of this, we can say a finite point set, has no limit point, because again in a similar region we can give the limit, has no limit points. Okay.